Hello and welcome, everyone. We are in, oh my goodness, we are in week 7. That's amazing. Week 7, and we are talking about models. So we are going to build off of all that foundational stuff, thinking about observations and data in that first kind of 3-week module, and then moving into sort of the theory and the science, the fundamentals of climatology, the physics and the math and the chemistry, all behind it, and it all comes together when we start talking about models. This is the key, right? This is where all of our projections and everything come from. It's also how we've developed some of that theory and some of that science that we've talked about for the last 3 weeks, as you'll find out, because well, like I say in all my maps and cartography and GIS classes, nothing gets people talking faster than a bad map. Nothing gets people talking faster than when you come up with a wrong projection. That's when the best science happens. When you come up with a hypothesis, you model it out and it doesn't work. That's when good science happens. When it works, it's like, oh, well, good, we got it right. That's great, but we haven't learned anything. It means that we validated what we knew. We haven't actually learned very much new. And so we're getting into the modeling side now. All right. So fun fact for the day, since everyone's talking about it, at least everyone in the rest of the United States is talking about it. My buddy Brian did a map to kind of highlight, just put in context, the recent cold snap that's hit, most of, most of the United States, certainly the central part, south part, the central, southern, and east coast. And he compared the current kind of blizzard type conditions to the coldest winter on record, which was, or the greatest cold snap, the biggest cold snap on record, which is in 1899. And it was about this week in 1899. And it shows the minimum wind chills, not temperatures, not actual air temperatures, but wind chills. So that perceived chilling effect, based on humidity and wind speed, observed during that period, and it's all been corrected for like modern understandings of wind chill and everything. And it's pretty fascinating, huh? So even in the coldest snap, um, you can kind of see the same kinds of patterns that are playing out now, right? We certainly had some chillier temperatures here. I've only been here 3.5 years and haven't really seen any kind of wind chills around 10 or 20 degrees even. So certainly seems chillier, but nothing compared to the interior. And so yeah, it's fascinating. It's kind of good to know that this is not unprecedented by any means, but it's also kind of cool to look at this and think, I wonder if that was an El Nino or a La Nina year. I'll be curious your thoughts on that when we meet in class. Okay, so we're talking about models, and you can't start talking about models until you talk about the conceptual models that I've been using this whole time. Right? This is a conceptual model. This is our understanding laid out in graphical form of how climates work. This is the first step, always the first step. Anytime you're trying to model something, you should always develop a conceptual model where you just draw it out. I mean, it's not rocket science at this stage. It's really, what do you understand? What do you think are the important components? And which direction are they going? And that way you can start to think about, okay, I'm going to model this way and this other thing this way, and I'm going to put it together this way. But it's not until you lay it all out until you can start to understand that. And so this goes for almost anything. I mean, I've spent, I don't know, weeks, months, years, even developing conceptual models. Yeah, years actually, for ecosystems. I mean, something as fundamental as that, like a boreal ecosystem in Alaska, and not even the whole boreal ecosystem, like subsets of the boreal ecosystem. And what are the most important drivers of that ecosystem? And man, I mean, just like I was saying at the beginning, I mean, nothing gets people talking faster than if you represent something differently than the way they think about it. And that starts the conversation. And this is why it takes years sometimes. So, conceptual models are always a really great spot to start. It can consume your entire time and your entire budget sometimes. But it's essential because, and I like this conceptual model because it really gets at all the components that have to be thought about in order to model climate. So think about this, and then think about, well, how you gonna put this into a computer, right? How you gonna do that? Well, it seems easy enough, right? Looking at the book, and it's like, okay, well, we'll just divide the world into some grids, and then we'll just apply this physical process model, right? We'll just say, oh yeah, there's some atmospheric conditions, and sometimes there's snow if the temperature's right, and if it happens to land on a continent, then it does one thing, it accumulates, and if it happens to land on the ocean, it does a different thing. And oh yeah, we got this, momentum and heat transfer, water transfer. We got in-column solar radiation hitting ocean differently in the continent, and then it's terrestrial radiation back off. And oh yeah, there's some sea ice, there's advection here. Yeah, but still, within any given grid cell, right? We can kind of just maybe one model for this, one model for this. We could do something as simple as this, right? In the ocean, we have a thermodynamics model that takes in solar radiation, emits back out terrestrial radiation, and we get oceanographic temperature, right? Easy enough. Not exactly. So first off, right, we have 3 dimensions. We have the X and the Y, but now we have the Z because of those darn Hadley cells, right? The fact that the energy moves across the Earth's surface in the X and Y, the northing, easting, up and across, right? But it also moves up in the atmosphere, the 3rd dimension. And that's a little bit more complicated, huh? And we start looking at these physical processes. It's like, well, okay, convection, snow, cloud covers. Well, that, like clouds don't just kind of form just in that one little grid cell over Mexico, or this little grid cell over Colorado. Kind of moves around, huh? And then you start thinking about some of the other processes that are happening. And then you get into something like this. Oh dear, that didn't represent very well, replicate very well. I'll just read off some of these. So this is scale in terms of spatial scale, and this is scale in terms of temporal scale. So spatial scale is how big of the process, or how much space does the process take, and the temporal scale is how long does the process take. And there's things like atmospheric turbulence, right, which is at the minute scale. That's the temporal scale, and it's at less than a kilometer. So atmospheric turbulence, right? I mean, you imagine when you're flying in an airplane and you hit turbulence. It's a pretty discrete little event, right? So less than a kilometer sometimes, or often. Same with atmospheric convection. Still pretty small scale, spatial scale, and at the minute to a couple minutes sort of temporal scale. Then you have bigger things like volcanic eruptions, last a couple of days, and they tend to be like 10 kilometers, right? So that's the sort of area of impact of that process. You have earthquakes, a couple of days across general big areas. You have seasonal vegetation cycles. Again, it's seasonal, right? And geographic. So it's not huge. Spatial scales, 10 to maybe 50 kilometers in spatial scale. And certainly that's seasonal vegetation changes, but also over time. So you get succession. So, a couple days, months, that kind of thing, right? Soil moisture, some synoptic weather systems, like the El Nino, La Nina, that's sometimes happening at a couple days. Or El Nino is actually more over here. So this is more just those high pressure systems, I should say. But those, have big impacts, right? Like over 1,000 kilometers, even though they're only a couple of days long, maybe a week long. And then you get some really big stuff out here, like species migrations. We're talking centuries, or soil development, or ocean circulation, like we were talking about last week, right? Just how slow those big, deep ocean currents are moving. I mean, those are 100-year, 200-year, 300-year kind of circulations. Same with CO2 under normal circumstances, right? And so you start to think about some of these key things. I mean, even glacial periods, those are hundreds to thousands or tens of thousands or hundreds of thousands of years. And we know all these things have dramatic impacts on the climate. So how do you start to model both the spatial scale and the temporal scale? So you're not talking just 3-dimensional models, you're talking about 4-dimensional models. That's complicated. That takes a lot of time, doesn't it? It takes a lot of thought, it takes a lot of programming. And this is why this is sort of the progression that we've had of climate models. You know, the 60s and 70s, when we were just starting to develop these models, or these computers that could run models and starting to code, and you know, coming up with these original hypotheses of like, oh, the greenhouse effect might be, you know, really impacting um, climate. You know, we started with just real simple stuff. This is off of a science blog. Um, excuse me. Um, So they start off with just atmospheric land surface kind of vegetation, you know, basically the surface kind of conditions, and they emit in the immediate interaction with the atmosphere and the ocean, right? And they just had these two layers. And then by the 80s, we got a little bit more sophisticated computers. We had more sophisticated hypotheses. We started thinking, oh, we actually need to couple this with, you know, kind of these separate out the atmospheric side, the coupled climate, in addition to the land surface and vegetation. We also have to deal with sea ice in the ocean, and that kind of got, you know, expanded out to include sulfate aerosols. This is like the big acid rain kind of time frame, but then also understanding the role of aerosols when it comes to producing precipitation. And then we said, oh, man, you know what? Vegetation changes with all these different changes. So we have to make vegetation interactive, and the biogeochemical cycles interactive. It's not just as simple as sulfates, adding sulfates in. It's actually this really complicated cycle. And then, oh yeah, carbon cycle. We know that we're increasing CO2 at this point. So we can't hold that constant either. So we added in those, and we added in these other aerosols and sea spray and dust and everything. And then we started, gosh, you know, ice sheets are changing. We have to include that. And so you can just see how increasingly complex, and now we're to the point where we're doing marine ecosystem changes, how that impacts not only the circulation and movement of temperature, but also that absorption of temperature and the potential release of deep water methane and those kinds of things. So it got really complicated, but it all started with this, just this simple model of energy balance, right? And you guys have seen this. You've done this actually. You did this in your exercise not last week, but a couple of weeks ago. You basically balance that energy balance model, right? That, remember the bare earth, or the, I can't remember what exactly it was called, but then versus the greenhouse gas models, and then kind of realized, oh yeah, there's these interactions going on. This is all this is, right? Inputted solar radiation, reflected and emitted. As simple as that. And then you kind of have this greenhouse component. Then you have, we went from that, you know, the simple global energy balance models to what's called one-dimensional energy balance models. And one-dimensional just means there's another strata, basically. And in this case, the most common one-dimensional ones were latitude bands. So basically, for every section of latitude, we would solve this kind of question: incoming solar radiation, outgoing reflected, outgoing emitted, for each section of latitude across the Earth's surface, right? And then we said, oh, but we can't just treat these as line models. That's what the book was calling, like line models. You actually have to transfer the heat then from this line model to this line model. So that's the one-dimensional movement. So basically, you know, being able to move heat up the latitude, kind of like what we talked about last week. So that's the next level of complexity, but it doesn't stop there, right? If we want to get to this point of having all those processes reflected, we have to go into something like this, where we think about the different axes of drivers that we're most interested in. And so this is a nice representation from Toronto, University of Toronto. You have surface processes as kind of one axis. You have the chemistry as one axis. You have dynamics and resolution. So those interactions between various components is another axis. And then you have radiation. And the most simple ones are kind of down here, right? Like the broadest, their coarse resolution, and they're simple, right? Like surface energy is really just about surface, or energy balance models really just about like surface processes, or one-dimensional radiative convective models are really just more about radiation. And you get like two-dimensional statistical dynamical models when you consider radiation sort of at a smaller scale in conjunction with, how things change across the Earth's surface, that kind of thing. Or you have Earth system model and intermediate complexity when you kind of start looking at the surface processes and the chemistry, and maybe a little bit of dynamics. It's kind of pointing in the middle of this thing. And then the highest level of climate modeling is high spatial resolution, where all these meet. So you've got dynamic, vegetation, interaction between radiation, surface processes, and chemistry, all at a small or a high spatial resolution. But it's also the most complex, as you can imagine, right? Think about those three-dimensional, now four-dimensional models at a high spatial resolution. Talk about that here in a second, the resolution piece. But just think of how complex that might be. And this largely matches what we've seen sort of in the science of climatology. And so this is a figure out of it's the National Academy Press's book on how to improve climate forecasting. But this is all using data from the IPCC reports, the Intergovernmental Panel on Climate Change reports. And what you see is sort of that progression of our understanding and ability to model things. So in the 70s, it was real simple: CO2 and rain, and then, of course, radiation. And in the 80s, we had it in clouds. It's not just rain. We have this whole reflected and albedo stuff, and ice, right? And then they said, oh yeah, we have like terrain too. So that's kind of important. And then FAR, so that was the very first IPCC report developed in 1990. FAR just means the first assessment report, I think is what it means. Something as simple as that. And at that point, they had all those, the clouds, rain, ice, terrain, CO2, and then they treated the ocean as this sink, basically, for temperature and CO2. Remember, we used to kind of think that the ocean would just absorb most of the CO2. And then the second assessment report, done in 1995, 5 years later, said, that's right. Now we need to model like volcanoes, because that has the real significant impact, and sulfates, those particulates, right? That are really important in the atmosphere. Plus, oceans are changing. We have like circulations and things like this. We can't just treat the ocean as sort of this barrel where it can just kind of accumulate CO2. It actually moves it around, and that has some implications. Then we got to the third assessment report done in 2001. And now we're really like thinking about, okay, carbon is not just emitted out, but sometimes it's taken back down, and it's actually coming from more sources than just people. And oh yeah, it's really complicated. And you have the overturning of circulation, like the changes in circulation, you have the aerosols, a lot of things. And then we have rivers, the changes the atmosphere, or the oceanographic chemistry, and that changes circulation. And so you can see that increasing complexity being modeled as we move through time. And then in 2007, the AR4, which is just the fourth assessment, I don't know why they changed it to AR instead of 4AR, I don't know, but now it's assessment report 4. That was in 2007. That's when they finally got the interactive vegetation, they got the atmospheric chemistry, just really sophisticated, complex things. You can also see the step in terms of resolution. So the first assessment was done at 500 kilometer cells. So this would be, I guess Greenland, right? And this is Europe. And then second assessment report, we halved it, so we doubled the amount of cells, and we got to 250 kilometer resolution. Yeah, it's better, maybe you've got some country definition now, right? In Europe. By the third, we're down 180 kilometers. Definitely looking good. We're picking up things like big mountain ranges, the Andes, big mountain ranges. So you've got up here, we're good, right? And then by the fourth, now we're really like looking much better, 110 kilometers compared to the 500 kilometers. Pretty substantial increases, right? Now we're at the fifth report that was developed in 2011, I believe. But what's significant about this AR4, the assessment report 4, was that was the first time that we started developing scenarios of climate. This is when we got to the first time that we got to not just single projections, which is what we are doing here. A single projection is just taking the trend and basically extrapolating out into the future. Fourth assessment was when we finally said, there's some assumptions that we're building in, and maybe we should vary those assumptions, especially when it comes to the carbon cycle from the human piece and how vegetation might respond. And if you remember back to when we were playing with Earth 1 and Earth 2, and I had you look at the A1F1 scenario, that's from this report, this assessment report 4. That A1F1 scenario was considered the most extreme on the high side of carbon emissions at the time. And so that's what you're using in terms of, carbon scenario for playing around with that hypothetical Earth. And so that was done in 2007, that AR4. The new one, AR5, was done in 2011. They've got, I think they have a new one, but we'll get more into that in a little bit later in the term. But this all gets us to, okay, so how are we doing this? If we've got sort of energy balance models, that is what we started off with, and we went into one-dimensional, and then the book mentioned the two-dimensional, which includes moisture and sort of heat transfer through the atmosphere. How did we get to the point where now we have this 110 kilometer resolution that includes chemistry and interactive vegetation and everything? And this is how we developed global circulation models. We developed these ridiculously complex grids that are in 4 dimensions, right? So we have the three spatial dimensions, X, Y, and Z, if you want to think about it in terms of a graph, or just north and east, north-south was one direction, east-west is another direction, and elevation is the third dimension, right? And so for each grid within that X, Y, and Z, we give it some base condition. Is it ocean? Is it bathymetry, so earth crust under the water? Is it terrestrial, earth crust above the water, like mountains and stuff? Or is it just simply a slice of the atmosphere, right? And there are, I think in the modern GCMs, 27 layers in the atmosphere, in which case at which scale they actually move energy from one layer to the next. And so this is from a more traditional climatology book, but then I went out and I found this one from sort of a popular science, this Rudiman figure, a popular science book on understanding climate. It was written a long time ago in 2000. But I love this diagram because basically for every single spot on Earth, right, you've got this box, this three-dimensional box in which you're thinking about individual three-dimensional boxes representing, like I said, either the Earth's crust or the ocean or the deep ocean versus the shallow ocean, right? And for each of those, you have like heat transfer and water transfer. You have a momentum, so you have movement this way as well as up. You have movement from the land onto the ocean. And then once you get up to the point where you're above the surface, then you have these layers of the atmosphere working differently to move water vapor up or down. You have the radiation hitting every single cell, right? And moving from this cell down to this cell, down to this cell, down to this cell. And then you have emitted radiation coming off the terrestrial back up into this cell, into this cell, into this cell, interacting with right? Weather systems, moisture levels, water vapor, and all that kind of stuff. And it doesn't just go up and down, it goes side to side, right? In the north south and the east west directions as well. And it all changes. Every single new three-dimensional cell is a different context. Crazy, right? This is a global circulation model. This is GCM. So when you see GCMs, it's global circulation models, not global climate models. That's often the mistake that people make. It's global circulation models because we understand most things are circulating around the Earth, and we're trying to model that, not just the what we imagine to be our climate. It's the circulation, is the movement of energy and water and aerosols across the Earth and the atmosphere. So this begs the question: how do we do this at a resolution that makes sense? And this is really, really important. This is something that for those of you who've taken GIS or remote sensing or even maps and cartography, I hit on this a lot because this is everything, right? I mean, we rely a lot on models for a lot of things in life, yet we rarely talk about resolution. And by resolution, I mean how much detail is there in these things. And so the best way to describe it is, I mean, I like the graphics from the book, right? So this is one depiction of North America. Kind of cut off Canada, but right, we've got North America here, and we've got a representation of the terrain. This is a 100-kilometer representation of the terrain. You compare this to a 10-kilometer representation of the terrain. And this is exaggerated. Obviously, it doesn't look like reality. This is to exaggerate, is there to show just how much difference a 1 order of magnitude in resolution makes when representing something as simple as elevation. And so when you think about global climate, global circulation models, and you think about our climatological systems operating at different scales and different resolutions, this is what you're always having to sort of balance. So this is 100 kilometers. This is what that AR4 report was generated at, 110. So if you look at this and you think about, gosh, that's really generalized. We need something like this. Well, that's true. That's absolutely right. This is very generalized. So this means that for every 100 kilometers, you get a new value for, say, air temperature from a global circulation model. So you got to drive 100 kilometers before you get a new value. So one value for temperature in the future is used to depict Ashland up to, Roseburg, right? It's about 100 kilometers-ish. One value. That's not accurate, is it? Well, it is when you're doing a whole global circulation, but it certainly doesn't help anybody in Southern Oregon plan for climate, because right now Roseburg is getting hammered, right? And we are not. Well, we're getting wet, but we're not snowy, and we're not crazy like that. Actually, I don't know if Roseburg is, but Portland and Salem sure did. So how do we get down to the 10 kilometer? How do we get down to something that's even better? And the book doesn't really talk about this other than discussing sort of regional climate models, which is great. Regional models do help out a lot. But they can't exist in isolation, right? I mean, you can't develop a regional one for North America and just say, oh, it's just North America, because stuff's coming from Asia all the time, right? This is the pattern in which climate systems and aerosols and temperature and water vapor move. It comes from Asia and it hits us. So how do you reconcile this? This is why we have this thing called downscaling, and hopefully you've heard this in the literature or in other classes, or in just reading about climate change. Hopefully you've heard about downscaling and making these things more realistic and representative of real landscapes, and not just at these really coarse scales. Because I mean, it's amazing that we moved from 500 kilometers down to 100 kilometer in the span of about 30 years. but now we're to the point where we need to adapt and mitigate and everything, and that requires a little bit finer resolution kind of stuff. So there's two forms of downscaling. There's statistical downscaling and there are dynamic downscaling. So statistical is the easiest in that it basically just requires you to go and do what's called delta change. Um, so imagine this is, each of these dots represent a grid cell from a global circulation model. So you have temperature and precipitation estimates and everything. For on daily, actually, they come out in, I think it's not minute. It might be minute time scale, actually. I was thinking it was like 15-minute time scale, but I think it's every single minute for every single day for the next 100 years. It's a lot of data, right? But that's the resolution they need, the temporal resolution they need. So imagine this is grid cell right there, or right here even. And it says it's going to be 5 degrees warmer. Let's say it's 15 degrees centigrade now. It's modeling that it's 15 degrees centigrade now. And in 50 years, it's going to be 20 degrees centigrade. That's a delta, that's a change of 5 degrees centigrade. So then you say, okay, well, this grid cell actually represents like this whole big different like landscape. And so if across this whole landscape, we're going to see a 5 degree centigrade change, well, what's the difference between here and here now? And that might be 5 degrees centigrade. And so then we kind of say, okay, well, we understand why it's cooler here because we have this adiabatic lapse rate and all kinds of things. And down here it's lower and we get inversions and all that kind of stuff. We can kind of parse out the 5 degree increase to say, well, actually, so most of the 5 degrees is going to be down here and the other part is going to be up here. So we might see something like a 7 degree change here and a 3 degree change there, or something like this. It could be reversed too. Totally depends on the context, right? But that's how they kind of downscale. So they kind of take the relative change within the grid cell, compare that to the relative change that the GCM is forecasting or predicting, modeling. And it kind of says, okay, well, based on this individual cell where we have mountains and valleys and agriculture, roads, whatever, rivers, this is how it would play out within this landscape. So it downscales it. And this is how we get it down to 10 kilometers or 4 kilometers even, which is what we have available for the whole contiguous US. We have 4-kilometer grid cells. We actually have some higher resolution stuff coming out very, very soon too. So the thing about statistical downscaling is that it does require some really good observation data, and for like everywhere that you want to downscale, right? So across Australia, that's going to be hard because people only live here, 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 and here. No one lives here. Very, very hard to get observational data, just like in Alaska, Canada, these other low populated places. So it requires enough station data that you can kind of capture this finer resolution terrain difference, vegetation context difference, so that you can do the statistical downscaling. But what's cool is that we have this really awesome example, and I want to show that to you real fast, just because I think this is going to be useful for some folks in perhaps well, I don't know if it'll be useful for this class, but certainly folks that might be taking GIS. But so this is the PRISM data group, and this is actually out of Oregon State, just up the road from us. They have been working, gosh, I can't remember when Chris Daly originally developed this. It was pretty cutting edge science when I was a master's student in 2005. Point is, he's been doing this for at least 15 years, maybe even 20. And you kind of look at the website and realize that, oh yeah, it's pretty old, but it's pretty remarkable. So what he's done is or his group has basically, they don't do the forecast, they don't do the future climate models, but what they do is they downscale all the previous kind of years or all the historical data, so that you can have this spatially continuous representation of temperature and precipitation across the United States, especially the contiguous US. He's got some data for Alaska and Hawaii too. It's not quite as updated. And so what you can do is you can actually go, I mean, you can read the methodology. And this is interesting if you're at all into statistics, because PRISM stands for, oh, here it is, Parameter Elevation Relationships on Independent Slopes Model. Basically, he has found a statistical way to kind of include mountains, rivers, everything, all the temperature differentials that you see when you move in that direction, plus distance from like coast and all kinds of things. He's found a way to kind of model that interactively for the whole contiguous US using GIS data and everything to estimate precipitation and temperature for every 800 meters for the last 30 years. And you can download this data. You can develop these nice little graphs. It's really, really cool. So this is like the climatological averages, right? So you've seen some of this data in some of the maps that I've shown you from my buddy Brian. You can kind of do these interactive map, kind of interactions, but if you're a GIS person, you can actually download either 4 kilometer. If you're looking across the whole United States, 4 kilometers great, but this is the stuff I always go for, 800 meter kind of stuff. I zoom into a state or two, and that's what I download. But then within a GIS context, you can absolutely do things like, what was the precipitation leading up to, say, a forest fire, and isn't that like amazing? Or what was the temperature leading up, like how much to desiccate and that kind of stuff. And that's all because of this statistical downscaling. It's simply statistical relationships that have been established, based on adiabatic lapse rates or whatever, distance from coast, applied so that you can kind of take these really broad scale 4 kilometer, 10 kilometer, 100 kilometer stuff and downscale it so that it's 800 meters. Pretty awesome, huh? The other version of downscaling is called dynamic downscaled. And so dynamic is basically that regional climate model. Honestly, it's saying, well, we're going to take the global circulation models and we are going to use those as the boundary conditions. Boundary just means when you move data from one cell to another. So when it enters that new cell, it's crossing a boundary. And so the boundary conditions are basically the information that's being passed to another cell. So you use the global circulation models as the boundary conditions, and then you run these climate simulations at a finer resolution. Regional, and they're called both regional climate and regional circulation. I don't know why they call it regional climate. I guess regional climate makes more sense than global climate, but yeah, they call them the regional models. These dynamic ones, though, are so computationally intense. Like these delta statistical ones, fairly accessible, fairly by meaning like you only need a couple of supercomputers to do this. The folks that did it in Alaska, who I worked with, they had 3 or 4 supercomputers, and they were able to do this delta dynamic or delta statistical downscaling for Alaska climate data, which was awesome. But they still required some supercomputers. I have a colleague up there who does dynamic downscaling, and the finest resolution he can get, and he's got 2 supercomputers he can access. The finest resolution dynamical downscale he can get is 25 kilometers. That's how much intense. So in Alaska, they've done this delta downscale down to 2 kilometers for both historical and future climate. But dynamic is still 25 kilometers is the best you can do. And that's running models for, I don't know, weeks, basically. So it's basically encapsulating all those physical processes that I just kind of presented and we've been talking about for the last couple of weeks into a model, but that's just focused on a specific region. Yeah, even for the whole state of Alaska, it's still 25 kilometers. So it's still pretty hard to make, sort of adaptation plans off of dynamic downscaling, because yeah, it's going to be more accurate in terms of the physics, right? The movement of energy from any of those layers, from one layer down to another, or the processes that are interacting, like those are going to be better captured when you use a dynamically downscaled or regional circulation model. However, it's still 25 kilometers, and that's really tough to make adaptation plans with. I mean, that's sort of Ashland to Central Point. Well, maybe not all their Central Point, but Medford, right? That's still a pretty big grid cell. And whereas statistical can kind of take that dynamic downscaled maybe and make it even more real and capture the difference between, say, Ashland and Mount Ashland, or right, or just Medford and Ashland, or Medford and Grants Pass, right? You can actually do the statistical downscales off of the dynamically downscaled, and that's going to give you your best available, kind of highest resolution data. So that's how you get it to the sort of meaningful resolutions for adaptation, decision making, things like species adaptations and everything. That's kind of how we get there. So the next lecture we'll talk about then how do you ground truth or validate these models, how that's done, how it's reported, and then how it's used to sort of test out all these proxies, going back to the paleoclimate, how we know that our proxies are decent, or how we know the climate has evolved quite the way we have, using these global circulation models.